Hey, thank you so much for being here at SparkCon 2020. We are super excited to bring experts and authorities in so many disciplines for the oil and gas industry. We really appreciate your attendance and participation in this event. This is one of the things that we want to do to add value to your business, help your success and future growth, and anticipate that you're going to be utilizing this information for your team, your organization, and your community. So thank you and appreciate your attendance. Today we have a wonderful guest that will be talking about trenchless technologies. Dr. Duyvestyn is specialized. He's the practice trenchless leader, or the trenchless practice leader at Mach McDonald, and has been in the industry for several decades and has responsible for hundreds of thousands of feet of tunneling technology and projects that are trenchless for over 2.5 miles. And it's a record. And thank you so much for being here, Doctor. I really appreciate the opportunity. And what we want to do is allow you the opportunity to present some of these techniques, technologies, and where the future is headed for organizations that are using trenchless technology. Thank you so much for being here, and take it away, Glenn.
Thanks, Russ. So today we're going to talk about HDD, and we're specifically going to talk about risk management with HDD projects. So I like to say this is your presentation, not my presentation. So please, if you have questions, we can get to the questions at the end. We'll go through them and answer anything that you have. Today, what I thought I would do is just briefly talk about the HDD installation methodology, just so those who maybe aren't familiar with it can understand what we do with the method. And then we'll get into some of those risk management considerations, those being the design and constructability issues, and then some construction considerations in the end as well. So getting right into it, HDD is a 3 to 4 step process. Most people call it a 3-step process. I like to call it a 4-step process. And that fourth, or that inserted step, is really the swab pass. So if we look at these technologies or these steps in general, the pilot bore phase is the first step. We have a drill rig as shown here on the left-hand side of your screen. That drill rig is there to advance drill pipe along a design alignment from an entry location underneath any obstacle that you're drilling beneath to an exit location on the far side. We pump drilling fluids through the drill pipe. Those drilling fluids mix with the cutting, or come out of the drill bit, mix with the soil cuttings that we create, and that material flows back to our entry location during the pilot bore. And we basically then steer and track where we are so we can drill from point A all the way to point B in our exit location. Once we have completed our pilot bore, we typically put on a reamer on the exit side, on the right-hand side being your exit again, and pulling that reamer through the ground, again, pumping drilling fluids down hole, having those drilling fluids exit the reamer, mix with the cuttings to create a slurry that flows back to our exit location or our entry location, depending on where we are in the process, so we can remove enough of the cuttings from the ground so we can eventually pull in a product pipe. The inserted step that I like to call it is that swab pass. So once we've reamed our hole to the final diameter, we'll typically take a reamer that's undersized from the borehole, oversized for the product pipe, and we will then pull that reamer through the ground. We'll take a look at the drill rig effort, the torque, and the pull force to pull these reamers through. And then we can use that as a proving run to make sure that the ground that we've conditioned has actually been conditioned well enough to accept the product pipe that we're going to pull in as the next and final phase. Okay. This is just a picture here. As we pull that pipe in, we have a reamer, undersized usually for the hole. We have a swivel that allows us to rotate the reamer, and we use the drill rig to pull on this side, rotate the drill pipe, rotate the reamer. The swivel then allows the pipe to not rotate as we pull it in, and we like to try and pull the pipe from the exit side all the way through to the entry site in one shot if we can. This is just a picture of that pulling head assembly. Here's a big reamer. You can see with the big teeth there. That black device you see here in front of that pipe is a swivel, and we've got our product pipe here that we're pulling in. To transition large pipe into the ground, sometimes we have to use equipment to break over the pipe. And so what you see here as that equipment on a large job with a very steep exit angle on this particular project for environmental means, but we basically have to pick up that pipe so we can transition it into the ground so that we don't overstress that pipe before it goes in the ground. So sometimes we can get into some large cranes that are required for a large diameter pipe. Okay, oops, what's going on? In the end, this is what we want to see. We want to see the reamer coming out of the ground here on the right-hand side. You can see the orange or the yellow mud-caked reamer. You see the orange swivel here, and you see the product pipe, again, the photo on the right-hand side. We would then wash off that pipe, take a look at the coatings, and call the installation complete. In this particular project, you're going to see a casing pipe here. I'll talk more about that later on in this presentation and why sometimes we have those in the ground as sort of a risk management mitigation measure. But we will pull that casing out then afterwards, so we just leave the product pipe in the ground without any steel on steel contact. So that's HD 101 in what is 4 minutes. We're going to start looking at some of the HD constructability issues. And so when we start looking at HDD, we really need to start asking ourselves a bunch of different questions. Across the country, HDDs are pushed in certain areas more so than others. But sometimes we need to take a step back and really look and see if HD is recommended for the crossing or if there's a better method to use to complete a crossing in particular. We really need to understand the limitations of the HD method, what it can do, what it can't do, where the risks are, what's required to see or to stage the product pipe, so that we know if we're actually creating more environmental impacts with HD than we were if we were doing something else. We need to look and see if we can control and manage drilling fluids. That's pretty much the critical key in today's HD installations. If we can't manage our drilling fluids, we can't control them, and they come up somewhere else, that's a big problem. Depending on where you are, it can lead to shutdowns, delays, and huge project costs. We really need to look at the full risk profiles instead of looking at risks individually. That's a big deal too when we're looking at HD installations. We always like to start looking at installations that have similar lengths, similar depths, similar soil types, just to make sure everybody or what we're proposing can be done. Sometimes we have projects where we push the limits. Russ briefly talked about it earlier. We recently completed a 13,247 foot 20-inch HDD in North Dakota, and definitely a record. I personally don't like records, but we had no choice there. We had to get underneath a 9,500 foot long lake, and that was the best way to do it. So when we look at key factors, we're going to talk about geotechnical conditions, and you're going to see geotechnical conditions come up throughout this presentation. We're going to concentrate on topography as well. We'll briefly look at achievable bore geometries. I'll spend some time talking about depth of cover for drills, again, to try and manage and control those drilling fluids. But we need to look at staging areas too and what workspace we have available for us for our projects. If we have site access issues, even what's the historical usage of the areas? Are there any old mines that we have to avoid? And those type of things when we go through these. So when we look at planning and designing considerations, again, geotechnical conditions are number one. I'm going to spend a lot of time talking about that. We'll briefly talk about topography and elevation differences. Depth of cover, looking at the materials we're going through. A lot of people forget or don't realize that when we start doing longer installations, we have more frictional forces, more higher mud pressures than we would for shorter installations. So sometimes we have to increase the depth to go longer and longer with our installations. Then we'll briefly look at the hydraulic fracture evaluation and the design calc and what we can do with that to show whether or not projects are viable or not. So with geotechnical investigations, we're always asked, do we need it? How many boreholes do we need? Do we need land-based boreholes? Do we need in-water boreholes? How close to the alignment do they need to be? So I'll start answering some of these questions. With the geotechnical data, I always like to say that if we can get boreholes that are, or if we're crossing a river and the river is 500 feet across, sometimes we can get away without doing any boreholes in the middle. Sometimes we can do that all the way up to 1,500 foot crossings. But when you start getting into longer installations, sometimes you need to get a barge out there and drill holes down in the water to characterize the ground conditions. That's especially important if you have differing geotechnical conditions across an alignment, because you need to know really what you're going through So you can then determine whether or not HDD is the best way to go, where your risks are, and see how you can deal with it. Our boreholes are typically completed 25 to 30 feet off of our alignment on land or on shore. When we get into the water, sometimes we like to increase that to 50 to 75 feet off of our alignment, just because we never know exactly where those boreholes are being drilled. And we want to make sure that we don't create pathways for drilling fluid flow through our holes that we're trying to use to characterize the ground conditions. And so with that, we really need to also look at filling those holes with grout upon completion, so that we take away any flow pathways that may be present. Our geotechnical investigations need to concentrate on the risk factors. So if we've got loose or soft or soils, we want to start characterizing that. If we've got gravels, cobbles, boulders, poor quality bedrock, we really need to focus on that as well. So we're trying to identify those risks or the geotechnical materials, so we can see if we can design the HD installation in more favorable, proper ground for the installation. So when we look at gravels or just the geotech program in general, we're looking at the density of the soils, the consistency of the soils. We want to do lab testing so we can understand the percent gravels. We want to then take the results of these boreholes and assess whether or not we have any stability issues. If we have raveling, can we develop drilling fluid, or can the contractor develop drilling fluid management programs to deal with the conditions? Similarly, if we ever have like a high plasticity clay, we want to make sure that the drilling fluid management and the materials that are being used can deal with the swelling tendency with those, so we can try to minimize any risks and inadvertent returns really associated with any of the installations. When we look at bedrock, we're trying to characterize the type of bedrock. We really want to know the rock quality designation. Sometimes we get boreholes that show that the rock is really fractured, busted up, jointed. If it looks like gravel, typically it's going to behave like gravel. So sometimes bedrock can be just as bad as soil. And so with knowing all these different conditions, we can try to design the bore in more favorable ground conditions. When we do go out and do geotechnical boreholes, we like to throw them on the drawings, see where the HDs lie, where they're going to be encountered, give this to the contractor so they can understand it as well, so they're not just looking at a borehole log trying to figure out what depth they're at. And you can quickly see then if you have any risk factors you have to deal with, or if you're good to go where you are. The number of borings really depends on the criticality of the project. You can see here there's a Hudson River crossing from a few years ago. We completed quite a few boreholes here. And the reason why we did that was that there's an old buried historic channel that's full of gravels and cobbles that we needed to know where it was. So it took a lot more boreholes to define it, so we can figure out where it was to locate our bore in the most favorable ground conditions we could. I'm always going to preach on if anybody's ever heard me talk before, I always preach know your ground. Again, it starts with the geotechnical investigations. When we have sand silts, typically we don't have any real concerns with that. The only time we ever have any concerns is if it's in a very loose or very loose to loose state. And really that's because of drilling fluid flow and higher inadvertent return risks associated with those materials. When we look at clays, we want to know if we have any high plasticity or sticky clays, or if we have very soft to soft clays. Again, because the very soft to soft clays don't have much strength to resist the drilling fluid pressure. So sometimes we have to have increased depth or try to get below those layers so that we can create and design our HDDs to be as least risky as possible given the circumstances. With the high plasticity, what we need to do is make sure that we pass that information on to the HD contractors so that they can then develop their drilling fluid programs to deal with that plasticity issue, and so that they don't have any balling up of their reamers, and they can again drill it with as low pressures as possible and that type of thing. Gravels, cobbles, and boulders are a big deal for HDD. I would say the gravels, anything that's greater than 3/4 of an inch, tend to stay in the hole. We don't really get that material out, and so if we know where the gravels are, we try to get the gravels when we're on our approaches, entry and exit tangents. Maybe we put in casing pipe. We try to maintain our horizontal sections out of those materials as much as possible, especially when we have gravels over, say, 40 to 60%, because the risks go up with more or higher percentages of gravels with that. So when we look at gravels, if you look at this, the picture on the right-hand side, we have a fine-grained soil. I guess this doesn't work anymore. This used to have a cartoon with it, but for some reason it's disappeared. But in a fine-grained soil, that orange that you see there is a filter cake that develops that allows us to support the ground and maintain our drilling fluids in that fine-grained material so it flows back where we are. In gravels, when we have mud, the mud escapes, goes into the open pore spaces around the gravel, and we can actually lubricate those gravels. We could actually have gravels fall into the ground, and sure enough, we can have difficulty trying to create the pathway, condition the ground for our pipes to be installed properly without having any stuck conditions or damaged coatings and that type of thing. So if we know the ground, we can try to place our pipes in more favorable ground so that we don't deal with some of these issues that we're seeing with this. For gravels, if we have gravels near the surface here, we can actually put in casing pipes, as you can see here, and we can drill through that casing pipe and complete our pilot bore and ream through it. Typically speaking, when we have those type of installations where we have that outer casing, we'll insert a smaller centralized casing inside that hole so that we center the bits at the bottom of the casing so that if we're ever bringing tooling back into that casing pipe, it has a better chance of actually passing through the end of the casing downhole and not snagging it and busting off or twisting off or damaging the casing pipe. Okay. When we do pump our fluids downhole, sometimes they come out the big casing, sometimes they come out the low casing. Doesn't matter where they come out, we always just want to see them. When we have drilling fluid returns like these coming out of the ground, we know what we're encountering downhole. We can adjust our properties the way we need to. We can look at it visually and see if it's really thick, and if we need to maybe slow down, pump more, and thin out the cuttings from the fluids. But if these are what we call drilling fluid returns, if the returns ever stop or cease, and we're still pumping downhole, they're going somewhere. Eventually, they're going to come up to the surface where we don't want to. So as any good driller will tell you, they always want to look at the returns, monitor those, make sure that they maintain them. And we try to keep them as low pressure as possible so that we can have them flow back to us with the lowest pressures, less risk for inadvertent returns. If you ever do put in casing pipe, here's a really interesting photo. If you ever put in centralized casing, you really need to track how much you put in there because if you pull it out and next thing you know, you thought that you had 80 feet, but you pulled out 70 and you realize, maybe I just had an extra 10, or I didn't put in that extra 10 feet. That casing pipe, if it's not installed or not cooled after welding process and pushed down holes, sometimes you can have issues. And next thing you know, when you go to ream it, your reamer's snagging the casing pipes, and sure enough, you're creating ribbons of steel and trying to figure out what to do. And for gas pipelines, this is a big deal if this ever happens, because we never want to have steel and steel contact. And so we need to make sure that we're removing all the steel that we're putting down hole. If we ever have gravels on both sides, sorry, again, my animation here is not working. But if we have gravels on both sides, we would put casing pipe down through the gravels on both sides. We would typically bring in 2 drill rigs that you see here, one on each side, and they would drill their individual pilot bores and trying to intersect in a middle tangent, typically, or a defined intersection location. And then once the pilot bore is completed, one drill rig will push their drill pipe through the other hole, and they'll just ream it, sometimes with using both rigs to support the drilling operations. But this method here is called the drill and intersect method. It's a great method to reduce drilling fluid pressures too, because you can imagine any installation length is really halved if you're meeting in the middle, because the drilling fluid pressures that are being created as you're drilling, say from the left down hole, only have to flow back to that drill rig and not complete the full installation from point A to point B. With the drill and intersect method, one of the things you have to realize too is that there are additional requirements. The big one is that we need larger volumes of water, and we have water demands at both sides of the alignment. We need larger staging areas on both sides of the alignment. So on a traditional installation, we may have a large staging area on the entry site, And the exit side, we may be within the existing right-of-way of the project, or maybe we have a little bumped out section for that, where the drill bit comes out and then we put the pipe together and pull it in. But when we're drilling from both sides of the installation, we need the large areas on both sides so that we can actually complete the installation and set up the equipment that's necessary appropriately to drill from both ends. There is always a risk of a sharp bend where they intersect. So that's why we always try to intersect our installations or design it so we can target intersection locations in the middle of the installation as the horizontal tangent, as opposed to a curve or even an exit tangent, which we have done in the past as well. Those type of installations, you're steering in the vertical plane and horizontal plane. So the experience of the contractor and the personnel doing that, it's a little higher. The risks are a little higher with doing that because you're not just steering in one plane if you intersect it in the horizontal section. Drill intersect does require or carries a slightly higher construction cost. But again, the biggest, and that construction cost is typically anywhere from 15 to 20% we've seen on our projects. But the biggest benefit with the drill intersect is that lower drilling fluid pressures. Boulders, I would say that boulders are something that we typically don't want to drill through. This is an example of a picture from a project in Vermont a few years ago, or New Hampshire, I think it was. You can actually see a curve in that borehole. This was drilled, and this boulder was drilled in the bottom of the entry tangent in front of the rig. It was only 10 feet away from the rig when they first hit it, or 20 feet away from the rig when they first hit it. They tried to drill through it. When they started pulling pipe through it, the pipe became quite damaged because it brought in a lot of gravel and bound up there. So they ended up digging up the boulder and fishing the drill pipe through again, grabbing new pipe and pulling the pipe through and not having any issues. So, but boulders are typically what we do when we hit those. We pull back and try to redirect around those if we can, because there are some additional challenges with drilling through those. In bedrock installations, we're looking at whether or not the rock is fractured or jointed. The jointing, weathering, and fracture nature of the bedrock really gives rise to increased fluid losses. So the drilling fluids we're trying to keep in the hole may migrate away from us. They may flow in pathways and pop up several hundred feet away from an alignment, depending on how connected those joints and fractures are for the installations. Strength of the bedrock's not necessarily a problem anymore. You just need to make sure that you understand what the strength is for the project so that the appropriate tools can be selected from the contractor to drill with them. We've hit unconfined compressive strengths in the Northeast of up to 58,000 PSI. It does decrease productivity, so it's a lot longer, much higher cost. But for the most part, it's not as big of a concern as it used to be. Karst features can be an issue. Karst is something that we seem to be pushing our installations in more and more. And so if we have large voids downhole, if those voids are not connected, we could fill those with drilling fluids, continue our drill and not have an issue. But if we were to drill and we hit voids that are connected, you can imagine if you go to an HDD, start drilling, and all of a sudden your drilling fluids are lost to these voids. And some karst areas, the underground passages flow like rivers. And so those drilling fluids could actually flow long distances away from your HD entry or your HD installation, and sure enough, show up where you don't want them to show up. Okay, this is just another picture of another borehole here. You can see we actually had a groundwater river flowing on one of our holes that we drilled for a particular project. It's not the norm to do cameras, but if you know you have karst features for the geotechnical programs, you really got to make sure that your driller is watching those drops so they can understand where those voids are. And if you're doing a 5-foot core run or a 10-foot core run and you only bring up limited samples, you really need to figure out then what's missing. Was it voids that were soil filled? Was it very soft and it just turned to mush and disappeared, or are they actual voids? And so sending cameras downhole can sometimes help you with that evaluation, just to determine what type of conditions you're going through. Moving on from geotech to topography risks. Large elevation differences can be a big problem for HDDs. So if you're ever in mountainous areas and you're trying to do HDDs, and it seems like we're being forced to try to do this more and more. If you set up a drill rig at the high spot here on the left-hand side of the photo and try to drill down that installation, you can imagine when you get underneath that river, that drilling fluids for the pilot bore actually have to flow all the way back up to that high elevation rig. And so you have a tremendous amount of pressure there. The mud may actually start flowing up into the river and creating its own pathway if you don't have enough depth below the river. Similarly, if you're too close to the face of a slope, you may actually hit horizontal springs that then allow the mud to flow horizontally and show up at the face of your hillside. So you can have high pressures trying to do it that way. Moving the rig to the low side and drilling it from the low side, so the right-hand side to the left-hand side, by all means, you help and improve the drilling fluid pressures. But one of the issues you're going to trade off is that if you draw a line from that drill rig across to the other side of that installation coming from the top, the ground surface or that same elevation to the top of the hole actually is not going to have any drilling fluid support once you complete your pilot bore, because it's going to flush down here. All the fluid's going to drain to an equilibrium. And so you need to make sure that the ground here is self-supporting on that high side so that you don't have increased bore instability, raveling, where you can't create an open hole and maintain an open hole. And sure enough, you have issues with that. Another problem you could have with topography risks, aside from the dry hole, is key holing. So you can see here, the picture on the right-hand side, you see a big bore hole right there. You see drill pipe, and you can sort of see like the bore used to be up on top, and now that drill pipe has actually cut its own pathway down. And so if there's no mud there and your drill pipe is doing this, you could end up having issues trying to pass tooling through. You can have twist offs, you can have stuck tooling. So just a bunch of issues with that you have to be aware of. Similarly, if we're drilling from the top to the bottom, or if we're reaming and we've packed off the hole and we're building up volume in our HD installation, once that blockage clears, all of a sudden you could have a large volume of mud show up on your site, and sure enough, you start flooding your site, sort of like that picture there with the white drill cabin, where you have a lot of mud that has come up all at once, and you have to be able to maintain that and control it. It's very hard to stop it, so you just have to be prepared to pump it to storage tanks or deal with it in other ways. One of the other problems you can have too with unsupported bores, if you don't have stable ground, is that all of a sudden over time you've got groundwater trickling down. It could carry fines with it, and sure enough, you could actually create sinkholes that could become a problem for your installation, like these photos are showing here. I briefly talked about historical land use. More and more, again, we're being pushed to look at HDDs in areas where there's been active mining. And so knowing and understanding where those mines have been, where the elevations are, when we start looking at trying to cross drills from one side of a river to another side, we really need to know where these mines were actively mining so that we can see even if we can actually do an HDD. This particular project, the owner was hoping to start a drill on the other side of this road. So on the right-hand side of the road, about halfway in the middle of the page here. Again, my animation for some reason doesn't work, but that's right. And lo and behold, the exit or the entry tangent for our drill rig was going to intersect right through some of these pillar mining where the ground has collapsed, where they've taken out a lot of coal. And so we ended up switching it to a jack and bore across the river at a higher elevation that avoids all that. So we didn't have to go with actually doing an HDD. Sometimes we recommend doing open cuts where we have conditions like this just because of the risk associated with trying to do HDD or even a jack and bore beneath a body of water. Okay. When we look at bore geometries, a couple things we always talk about. We always talk about a setback distance. So you can see I've got an entry location on my right-hand side. I'm set back from the river's edge. I have an entry angle. I have an entry tangent down to my point of curvature, and then I start a curve, and then I hit a point of tangent where I'm horizontal again. That gives me a certain depth of cover beneath the river bottom. We always like to take a look at the elevation difference between the entry location and the bottom of the river. and the depth of cover and seeing what those ratios look like. Because often we find that we're reviewing others' work that designs that have low depth of cover and don't really have like a one-to-one relationship here, or maybe 25% of a ratio of a depth of cover divided by this elevation difference. We find that there's a large risk of mud wanting to come up into the river as opposed to flowing through the hole that we're trying to create. And so the only way to really look at that is to take a look at it from a constructability point, see what you can do to increase your depth, whether you're increasing your setback distance, maybe looking at steeper entry angles, maybe a combination of both, so that you can get an increased depth of cover, so you can get a better ratio when you start looking at the depth of cover and that elevation difference to the bottom. Because typically speaking, that gives you a better installation and an easier way to manage and control your drilling fluids downhole. When we look at controlling and managing and drilling fluids, we definitely do not want to see this. These are taboo, especially in today's market. One of the myths we always hear all the time repeated is that inadvertent returns are just part of doing business. Well, I personally would say that proper planning, proper design can you may not eliminate completely, but you can significantly reduce its occurrence. You can also, by implementing requirements for the contractor to monitor downhole pressures while they drill and track those to your estimated pressures, just to make sure that you're not creating thick mud, you're not creating a situation where you have higher pressures than what you really need to do a drill. So we can try to avoid these messes to the extent possible. With drilling fluid returns, we're always trying to maintain drilling fluid flow. If we have drilling fluid flow either to the entry or exit location, we have a less likely that they're going to come up in between. We definitely do not want to see inadvertent returns on HDDs, especially in the Northeast. That seems to be very taboo these days. And again, you'll be shut down, high fines, a lot of standby rates, a lot of increased costs associated with it. By looking at your returns, looking at your downhole pressures, allows the driller to be able to respond to any issues that are developing. With those returns also help with us removing cuttings, because again, we have to remove a volume of cuttings equal to at least the pipe, so that we can, when we pull in that pipe, we've removed enough cuttings so that we can actually get the pipe in the ground. We're always trying to condition the ground with our drilling fluids. We're always trying to cool the bit and help the bottom hole assemblies cut the hole. But it really comes down to monitoring those annular pressures and making sure we understand where they should be. One thing to note are the drilling fluids are lazy. They will follow the path of least resistance. We try to create that pathway with our HDD installations. But if we're designed too shallow, or if we have a different change in conditions, maybe, or soft soils, or just high mud pressures, sometimes they're going to try and create their own pathways, and that's what we're trying to prevent on an HDD. We don't really ever want to see mud come up where we don't want to, like these photos you see here. Okay. The highest probability of having an inadvertent return occurs during the pilot bore and the initial reaming pass while we're trying to increase the diameter. And that initial reaming pass really is because sometimes we create slugs of cuttings that can temporarily pack off the bore and increase pressures. But when we start looking at monitoring pressures, typically speaking, we're just looking at monitoring the pilot bore operations because that's the highest risk component. So here we have a good picture of drilling fluid flow coming out of the ground. You can see in the pit here, the more lighter gray colored or greenish gray colored drilling fluid, that's your fresh mud. This grayer, darker gray cuttings or returns include some cuttings that we're producing here as we're cleaning out our casing pipes. When we go to the next slide here, you can see here we have really thick mud coming out of the ground. So just by looking at the mud too, you can tell if you have thick mud or if you have thin mud coming back. Obviously, the pressures for thick mud are much higher, so you have a much higher risk of mud coming up where you don't want it to when you have mud that is really thick coming back like this. So even visually, you can take a look at this, and maybe you want to increase your pump rate, slow down your production rate to try to get more fluid per cutting so that you can maybe lower your risk of having mud come up where you don't want it to. I'm just going to go through and briefly here and talk about ways of managing, controlling drilling fluid flow and show you that there's a risk of inadvertent returns on every HDD. So here we're at point A, we're doing our pilot hole drilling. We're pumping mud down the yellow middle stem. That's our drill pipe, exiting the drill bit, and it is flowing, mixing with the cuttings and flowing back through the annular space back up to our ground surface at A. And this is how we create that path of least resistance for our drilling fluid flow. When we get to B, assuming that we have the proper depth of cover beneath our critical feature, we're still pumping mud down through our drill pipe. You can see that coming out of the orange, comes out of the bit, mixes, and still flowing back through that annular space back to our drill rig. When we get to C, we still have drilling fluid returns coming back to the rig, but we do not have the path of the bore drilling up to the ground surface. We're creating that with our pilot bore. And so as we get further and further and further along and start steering further up to the ground surface, eventually we get to the point where we're at D, where if we're still pumping mud down, all of a sudden we have no return fluids. And if we keep pumping mud, that mud's going to come up. And sure enough, if we keep pumping it, it's going to show up at the ground surface, and we have an inadvertent return risk. And then this photograph I'm showing here at D, we're actually underneath a highway here. So if this risk occurs on every HDD, because we always have to exit our installations. So if we ever had a critical feature like a highway or a wetland there, one of the things you always want to look at doing is taking that exit location and maybe moving it further away, so that if this mud does find its way up, it's not finding its way up underneath the critical feature. But this drilling fluid analysis or demonstration, if you want to call it that, shows you what we mean by an inadvertent return, and that this risk occurs on every HDD because we always have to exit the HDDs from the ground surface. We can predict those. Here is a hydrofracture evaluation. We use these in our designs all the time. Just to go over the different colors of the lines. The green line you see, that is the dashed green line is your ground surface. The black line here is your HDD alignment, okay? Your dashed orangey brown line that's down at the bottom or in the middle bottom section, that's your overburden stress. We use a Delft Geotechnics approach, Army Corps of Engineers recommended method for crossing levees to figure out the theoretical formation pressure, which is the red line. And then what we like to do with our red line, because that sort of suggests that's where the failure line is, we'll put a factor of safety on it and then come up with a recommended allowable pressure for the drill. And then when we do our evaluations for what the required pressures are, which is that blue triangle line, we try to make sure there's adequate separation between our required line and that blue line so that we can accommodate pressure spikes that are created as we drill from point A to point B. If we're in sand, sometimes the pressure spikes aren't that great, but when we get into sticky clays, we can have huge pressure spikes, and I'll show you that here in a second. So typically, even though I showed you a red line, that theoretical line in this back slide here, when we go to design, or into construction, sometimes we are asked to produce these charts for the contractor, and so we will give them the required pressure here as opposed to theoretical. Because if you give them the theoretical, some contractors always think that they're going to be able to drill up to that when we want them to minimize the risk of inadvertent return. And the best way is to establish that recommended maximum allowable pressure below your threshold that's going to give you fluid pressures. Cool thing with this is that anytime the required pressure is above the total stress, you can see exactly where you're relying on the strength of the material to resist your drilling fluids and where you're not. You can see too on this installation, I'm drilling this from the left to the right. So my blue line is increasing from 0. And as I drill and as I exit and come up to my exit side on the right-hand side, I still have a flow component all the way back to my drill rig. And that's why on the right-hand side, it never falls back off to 0. Okay. When we're drilling and we're monitoring those drilling fluid pressures, we like to plot them and see how we're tracking to our installations. We can see where we're maybe getting above, where we have pressure spikes. We're always in communication if we have inspectors with the contractor, because the contractors never want to have mud come up and it's just another set of eyes. So we always work together as a team trying to make sure that we do our installations without mud coming up where we don't want it to. When we're circulating mud, we have much lower pressures. You can see that here, as opposed to when we're drilling our pilot bore and actually creating new holes. Sometimes in this particular project, we were going through some shale bedrock and some clays that wanted to swell up and ball up. And so we had a lot of pressure spikes. That's what you're seeing here on this graph. And then on this graph, you're just seeing the circulating pressure after we completed our joints and cleaned out the hole. You can see they're a lot lower than what they were. When you're looking at inadvertent return risk factors, this is really from an engineering standpoint, but if you have inadvertent returns, typically speaking, when there's an insufficient depth of cover, maybe the installation length, whoever put the project together didn't realize that if you have long installations, you have to be deeper because of that frictional flow component, higher pressures to make the mud flow longer distances. Large elevation differences along your alignment can dictate your pressures too and what's required to overcome the hydrostatic pressures in addition to the flow components. Unknown geotechnical conditions can be an issue. That's why we always like to go out to our geotech programs, make sure we understand where the risks lie, try to mitigate them as best as possible. We try to avoid those unfavored ground conditions. Layered soils are a big deal. That hydrofracture evaluation that I showed you there with those chart, not developed for layered systems. They're developed for one soil type, so you really need to look at your soils. I see it often where somebody's designed a drill that's 100 feet deep and they have 80 feet of soup materials and they have 20 feet of good soils and they treat the entire 100 feet of depth of cover as good soil. Well, you can't do that because once that mud finds that soft soil, there's no more pressure required to have it come up to the ground surface through those soft soils. So you really need to be careful on how you treat your soil properties. And that's where I have bolded here unrealistic input parameters for the hydrofracture calculations. If you want to give the soil concrete parameters, you can make anything look good, but you really need to be realistic in how you pick your parameters to create those charts. Okay, because there's often a lot of reliance on the strength of materials, and you have to really understand that if you're relying, if your drilling fluid pressures are 5-6 times the total overburn stress, that's probably relying way too much on the strength for an installation to be successful. Okay. Again, typically speaking, from my perspective, when we're brought in to help out with projects that have some issues, we see that there seems to be a lack of knowledge of hydrofracture evaluations, where they can be used, when they're used. A lot of the time you have a drill, mud's coming up everywhere. The first thing you can ask, okay, well, where's your calcs to support the design? Oh, none were completed. Well, then how do you know something's been done properly? You really need to do those hydrofracture evaluations as part of your design so you can make sure you understand what the thresholds are and whether or not you're designing something for a contractor that can actually be completed. In the field, if you respond slowly and you see pressure spikes and nobody's paying attention, sometimes those spikes can lead to mud come up to the surface before you get a chance to respond. So if you see pressures spiking above where you think they should be, if you see the return slowing, you need to, the good operators will stop, slow down, maybe clean out the hole a bit, swab back, try to re-engage the soils to make sure that they keep the pressures as low as possible. One of the issues we've seen too lately is that there's a strict list of approved drilling fluid additives, and that strict list sometimes doesn't allow you to do some of the fluid property modifications you want to meet with a certain type of soils that you're going through. When we look at curved sections and straight sections, obviously when we drill curves, we usually cut holes closer to the bit. When we're doing straight sections and we're rotating the drill pipe and the bit, sometimes we get a little bit higher or larger diameter bores. But a lot of people often will say, we'll try to assess the hydrofracture evaluations based on overinflated bore diameters than what the bit they're using. So that can also lead to a perceived feeling that your drills are okay when you actually have a high risk installation. Okay. When we look at construction here, details, we just got a couple slides left, but what we like to do is make sure that you have a good design and that you have a comprehensive HD specification and that you have a comprehensive bid package that you're receiving from a contractor so you can look at the equipment, maybe even assess the work plans at a bid stage, and then reevaluate upon award. That allows the contractor to give you some general stuff for the bid without spending any money or any real effort. And then once you've awarded the project to your successful bidder, you can then get the details you want for your project to make sure that they're site specific and that it's been reviewed. A lot of times people just take the work plans and just dust them on or just throw them on a shelf. You really need to look at them, make sure that that you have them, that they've been reviewed and that they're fit for the installation that you're looking at. If you've requested downhole annular pressure monitoring, you better make sure that that's in the work plan. Otherwise you get into some issues there as well. My experience is that most of the contractors don't read specs. So if there's anything that is really, really important, you need to put it on the drawings so that they actually see it and can deal with it. Because they're more likely to read a drawing than they are to read the HD installation specification. Again, I said that already. Comprehensive work plans are required, need to be reviewed. They need to be site specific. They need to outline contingency plans. What are they going to do if drilling fluid pressures are higher than they anticipate? You know, all that type of thing, just to see what we can do to try to lower the risk for an installation and decrease drilling fluids coming up where we don't want them to. When we get into construction inspection and monitoring, typically speaking, we like to look at the HD rig parameters, the drilling times per pipe or joint, the drill rig thrust, torque, the mud pressures, the flow rates, the mud pressures, looking at the drill pipe pressures, but also the inlet pressures downhole, so that we can track those against those charts to make sure that we're following a path that is similar to what we predicted with our numerical or our hydrofracture modeling. We also want to make sure that we're looking at the pilot bore path, checking it for the radius to make sure the radius is being drilled the way it's properly supposed to in accordance with the requirements for the project, that you're not too far left or right, that you're within your easements, your elevations look right, your depths. And whenever the mud properties are collected, we like to record those as well, just so we have a good record of what's going on. The spoils, often you'll see contractors or folks talk about the soil they're having, and it doesn't sometimes match what you see in the separation plant. So having photographs is helpful there as well. And we always want to look for drilling fluid returns and help out as much as we can. If you ever notice the drilling fluid returns are stopping and the contractor maybe, or the drill rig operator hasn't seen it yet, you might want to speak up and just tell them, hey, your mud's slowing down. You might want to, and then it allows them to react to it quickly and go from there. This is just a picture of a data sheet that we collect showing all those things that we just talked about. We even like to track the steering data in the middle of how they drill their pilot bores. And that is it for the presentation. Russ, I don't know how you open it up for questions.
Yes, we have a few questions here, so right. Let's wrap it up and look for a few questions. So one of the things that came across was, what fluids are used for HDD? Is it the same for fracking?
So fracking for oil production is a lot different. For HDD, we use water-based fluids. For fracking, they typically use oil-based additives. So ours are usually bentonite, which is a common clay material. We use some other non-toxic additives so that we can get the properties we want, what we can't get with bentonite alone. Some projects we have to have NSF 60 certified fluids, which are the same fluids they use for drinking water wells. So then you know that you're not creating or adding contaminants. But our fluids for HD are a lot different than they are for the oil field and production well drilling.
Okay, that makes sense. Also, is HDD the same thing as fracking, is one of the questions.
So, yeah, I would say no. The public sometimes thinks they're the same. When you look at directional drilling, they think directional drilling and HD are the same. Different terminologies loosely used, but when we're talking about fracking wells, you're talking about drilling down and doing directional changes and drilling different pathways that are never come up to the surface, and they're just there really to try and split the rock and get more oil out. For HDD, we're starting on an entry location, we're coming out of the ground, our exit location, and we're trying to install pipes, so a little different.
I have to imagine on the larger diameter runs and some of the larger projects, when you're talking about the the pilot drilling, and then is it incrementally go up, or do you typically have to graduate those those pilot holes in the process over time, or because some of these larger pipes and diameters I have to imagine that there's a process that you have to go through?
Yeah, so there is a process. If we have a large diameter pipe, and let's say we're doing a 42-inch installation, for example, a 42-inch installation typically goes into a 54-inch reamed hole. And so our pilot bore diameter for the larger rigs are usually around the 12.25-inch diameter. And there are projects where we go from that 12.25-inch diameter all the way to a 54-inch ream in one pass. Depends on the ground conditions and how risky and what the type of material we're going through. But typically speaking, they'll step it up. So they may do a 24-inch ream, a 36-inch ream, and then a 54-inch ream, something like that, where they step it up as opposed to going to the final ream diameter in one shot.
And then on the placement and the position of the drill, the entry and the exit, how do you calculate distance? I know there's a lot of geological analysis that goes into it, and it was fascinating to me because I'm not involved in this piece of the industry, and it's how much site work has to be, how much drilling time has to be broken out, and what does the total project duration look like as in phases, in those different phases typically?
So typically on the larger projects where you have multiple installations and maybe open cut between HDDs, the HD contractor is a sub to a prime contractor. So usually the prime contractor will come in, they'll do the clearing for the site, they'll do the clearing for the pipe staging, the pads, they'll bring in matting, they'll do silt fencing, all the controls they need for the sites and set up the site so that the HD contractor is just coming in to drill the hole. The prime contractor actually even does the welding of the steel pipe and supports or has the equipment to support picking it up so that the HD contractor really is just drilling it and then pulling it in. And most of the other activities are done by the prime contractor. In terms of schedule, it really depends on how long you're drilling, what material you're going through, the size of the pipe. It all dictates on whether you have a project that's 2 weeks, a week, or if it's 4 or 5 months.
So it's project by project basis.
Yeah.
So, which makes a lot of sense. Now, there's some other things that I wanted to, let's see, it looks like we have a few other questions here. Let me bring them up. Does the product pipe need to be pulled in one continuous pass? So
it doesn't have to, but if you can, your installation loads are a lot lower. And a good example, the more pipe you have in the ground when you stop to do another weld and do that intermediate weld, because you can't stage your pipe in one shot, the installation loads to get going again can be really high. If they exceed the rig, you're stuck. If they're high, usually you can break that bond and then they'll lower out. But you need to keep that time that you're welding your different pipe strings to the least amount of time as possible. We've even had projects where we've done the welding, moved the pipe a bit, then coat it and test it so that we can keep the pipe moving somewhat so it's not sitting long term and having that mud gel up and sort of stick against the pipe. That 13,247 foot installation we did in North Dakota, we had 3 welds. When we stopped to do, we had 2 welds, 3 sections. We had 7,500 feet in. We were basically welding up the other 600 or 6,000 foot string or last string. For us to get going with 7,500 feet in the ground already, we actually had 850,000 pound. So if our rig was any smaller than that, that pipe would never have been completed. We had a 1.2 million pound rig and it pulled at 850,000 pounds for that moment. And then all of a sudden when it started moving, the loads came back down to the 400,000s where they were beforehand, and we were able to complete the installation. But that's a big thing to realize, that if you are stopping to do welds, depending on your length, depending on your pipe diameter, you're adding risk to your installation.
Yeah, if that pressure exceeds the ability for that rig to pull,
yeah, that
could run into a challenge.
Right.
So I know that you outlined several of the challenges and risks involved in this. Is the technology in the future, is it evolving to the point where it's increasing, improving, or reducing risk? Or is it, what's the roadmap you see in the future for continuing this process for, as we, freeways and roads and rivers and obstacles and building infrastructure? It really
I would say in the last 10 years, the industry and the regulatory agencies have pushed us to use HDD almost as a go-by if they ever have a creek or a river crossing. And that has led to some serious failures, using it in conditions or ground conditions or just environmental impacts that are much greater with looking at an HDD than doing a traditional open cut. And I think nowadays, some of the regulators are realizing that HDD is not the silver bullet, can't be used everywhere, should not be used everywhere. And really, it's just a tool in a tool bag, and you've got to figure out where you need to use it, where you don't use it. Looking at the future, I would say that we're seeing longer installations. We're seeing larger rigs. It just depends on what you're trying to do with it. But anytime you can make your installation smaller in length, it usually can be shallower, and so there's less issues associated with those typically. And so doing that approach really helps mitigate some of those risks with what you're trying to do.
Yeah. I just really appreciate all this information, and I know it's a lot of information. So anyone that's involved in SparkCon 2020, thank you, Doctor, for your all your efforts, and I appreciate all of the information that you've accumulated over the years and the experience that you have and the things that you've shared today. Really, truly appreciate all of this information. And I know that there's so many individuals out there that are looking and searching for some of the knowledge that you've been able to transfer to us. And as we go through this process, we'll wrap up and we'll continue to share this information out and share all of the valuable technologies that are coming about and some of the risks and the strategies you need for your business. So there again, Doctor, thank you so much. Mott McDonald and SparkCon 2020 is looking forward to the next episode coming up soon. And anytime you need information, reach out to the team. Make sure that you have the information you need to provide you a roadmap for your success in the future in 2021.
Great. Thank you.
Take care.
Right. Bye-bye.